Hello everybody, welcome to Introduction to Deep Learning. Today we're going to talk about data augmentation and advanced regularization. So in the previous lecture, we have spent a lot of effort on loss functions. We have spent effort on generalizing binary classification, such as using, the sigmoid, which is basically a binary probability. So it's either, so it squashes it to 0 or 1. And then the probability, basically, it can be interpreted as a probability. So if you have more than 50%, then it's this class or the other class, respectively. And what we have done is we have basically generalized this binary classifier to a multi-class classification. We have introduced the softmax formulation, which is essentially modeling the probability of the classes with a generic number of classes. So the idea there was we have this normalization and we have this exponential function, which is this soft max. So it's kind of approximating the maximum function, but we still get gradients. So the idea there is we have this exponential operation. We make sure the probability is greater than 0 and has this short fall off, yet still being smooth. And the second thing was we have the normalization. So we're making sure that all the probabilities sum up to 1. The next thing we talked about was we talked a lot about activations. Specifically, we analyzed why certain activations are better or more suitable for certain cases than others. So for instance, here we have the sigmoid activation, and the whole point of the sigmoid activation was that, well, if we are in this regime of the extreme cases, we have basically almost no gradients. And if we have very little gradients, then we can't learn a whole lot. And this is the problem, and the remedy for that was this ReLU idea. The ReLU idea is simply a max function. It's a very simple activation function. It doesn't saturate such that we always get good gradients. However, we have dead ReLUs where we are in this realm, we get also no gradients, and we have to figure out what you do there. And on the very high level, what we have talked about is we always wanted to make sure that we have good gradient flow, right? So we wanted to make sure that we have a deep network, we have many layers. We would like to figure out always to have gradients that are flowing through the network. And through that, we can basically get a good training procedure and we can converge to a good solution. So one part of that was, of course, the activations, and the other part of that was the initializations. So we talked about how do we make sure that the distribution of the activations essentially doesn't change across the layers, right? So we wanted to make sure that roughly the input and the output of a specific layer should kind of model the same distribution. And the idea here was that we initialized it such that the initial weights don't bias that. And we talked specifically about this Howey and Cumming initialization. So the idea there was, well, depending on how many neurons we have in a certain layer, the variance is then set over, randomly initialize the weights, right? We have it zero-centered, and the weights are initialized, are drawn from a Gaussian distribution with a variance of 1 over n. This 1 over n, however, has the issue is if we're using ReLUs, then the activations are being cut in half. So we have to just by a factor of 2, which is essentially what this Cumming initialization does. It just sets the variance where we're drawing our weights initially from to 2 over n. And this is basically being used all over the place right now, and it's pretty much the standard. Today, we're actually going to follow up on that. More specifically, we're talking about data distributions a little bit more. And in this previous part, right, the idea was that we wanted to make sure that if we're using activations and weight initializations, such that we don't diverge in terms of distribution throughout the layers. And what we want to do today is we want to build on it such that we also enforcing certain distributions between training and validation, but also we want to make sure that our input distributions we are understanding. And one specific idea of that is data augmentation. And data augmentation, of course, many of you will probably recognize in the context of, we're overfitting, so we have to do augmentation to remedy it. That is one part. But it's very much related to these distributions of the data that I've just mentioned. And one specific part of that is actually how we pre-processing the data, right? So basically, what we have done now is we have talked about how we initialize weights, but we have not talked about how we deal with the data itself. And one specific part here is that we would love to go ahead and enforcing a certain distribution such that it's easier to learn it. Well, what does it mean? Well, for instance, if I take an existing network and I am taking the input data and I'm multiplying all the input data with a scaling factor of 1000, right? So all the floating point values in, let's say, an image or so, every pixel value will be just multiplied by 1000, right? So obviously that would be a problem for certain reasons. So meaning that all the regularization and the learning rate weights, they would just be distorted relatively speaking. By the way, that's also something you should be aware of. If we're going ahead and scaling essentially data, the network could learn this, but it might be difficult to learn it because it might run into local minima. And even if it does learn it, basically by scaling the data, you're changing the weighting between the learning rate and the regularization effectively. So this is something you have to always keep in mind when you do that. And the idea here of pre-processing is basically to normalize everything. And well, normalizing means a lot of things. There's a couple of things what we would love to do here. And one thing what we would love to do is we would typically mean center the data, right? That's kind of obvious because we want to make sure that we kind of map to this canonical distribution. So this is the zero centering what you do. So you're computing the mean and you're subtracting the mean across your data distribution. And the argument is, well, it's easier to learn if we are basically having a mean zero-centered distribution because then the weights don't have to deviate too much. They don't have to do as much at the beginning in the input, and that makes the learning easier. That's one part. The second part what we care about in the input is we would like to make sure that our dimension, like all the dimensions of the input data, they don't have any outliers. So this is this normalization here, right? So we're going through all the dimensionality of our input features, and we want to make sure that they are all at the same scale. And this is not a new idea. People have been doing this in machine learning long before neural networks. There's ideas like whitening and stuff like this. So basically you're computing variances and you're dividing by the variances across each dimension of your features, such that you're getting these mean-centered distributions that are uniformly distributed across its dimensions. And that's what we want to do here as well, right? So there's these two parts. There's the zero-centered, which we've just talked about, and there's the normalization afterwards. And these ideas are, well, technically there's no augmentation at this point yet, but these are actually pretty important because we want to make it as easy for the network to learn certain things and taking the burden of having to deal with the inputs right away. And if the input actually has some outliers right at the beginning, this is always a very, well, precarious situation at the beginning when you start training. And you see this very quickly when your loss doesn't change the way you want it to be, then sometimes there's something wrong in how you're pre-processing the data to begin with. Okay, so data pre-processing should kind of make sense to you, right? Like the zero centering makes sense, and also the normalization of the data also makes sense because that makes it then easier to assign and optimize for the respective weights accordingly. Okay, now let's talk a bit about data augmentation. And I mentioned already that a lot of people think about data augmentation as a way to regularize, and that is true. But data augmentation has a very simple idea. So for instance, if you're talking about a classifier, what we would love to have is, we would love to have this classifier to be invariant to certain transformations and operations that are applied to an image, right? So for instance, if you just go ahead and search for a cat image on Google Image Search, you will notice that all of these images that you're going to find there, they have certain transformations applied. And the extreme transformations are something like go from a drawing to a real image. And that is something that we would like to deal with by saying, well, we would like to basically have this augmentation as part of the training. So in other words, if that image is in a certain, there's a certain transformation to be applied, our network should give you basically the same result in terms of the scores and the classification results. And that's something we would love to do. Now, the problem is, of course, like our training data might not cover all of these transformations for all of these images, right? So for instance, for our training data, I might have one image that looks like that and another image that looks like that. So these are obviously different images, but if I could go ahead and transform this image to this image, and I say, well, I want to be invariant to this, I would just make sure that for every image that I have in my training, I can apply all of these transformations at the same time. And this is the idea of data augmentation. Right? So we want to make sure that all these invariances we want to learn from our data distributions. We would like to synthesize these transformations such that the network gets it, even though we don't have the necessary training data for it, right? So obviously, it's not going to be covering all kind of transformations. Some of them are a bit easier to do than others. So for instance, lighting changes is very difficult to simulate, right? If you want to take an environment and you want to capture an image from that environment, and then you want to change the lighting of that environment, well, yeah, our classifier, we would love it to be invariant to that, but it's very difficult to synthetically change the lighting of an image. In fact, that's a whole research direction on its own. So if this could be done, that would be very nice, but it's not that straightforward. So what we do most of the time is we're going to start by data augmentation by looking at very simple things that we can simulate, and it doesn't need to be too complicated. So for the most part, when we're talking about data augmentation, that's actually stuff we can even do on the fly. So you don't typically pre-compute the augmentations, but you actually, in your data loader in PyTorch or so, you just load an image, you apply a random augmentation, and then you train on that image, right? That's typically what you do. And these augmentations are relatively straightforward, meaning that the compute should not be too heavy while still having an effect of representing to a reasonable level augmentations or transformation operations that you will see in real-world data distributions. Okay, so let's have a few examples here, right? So what's simple? Well, okay, let's say we have a simple image, looks like that. If you're flipping the image, that's the simplest augmentation you could imagine, right? So I just mirror the image. I take this image here as input. I flip it. I just mirror it across the y-axis. We would all agree that doesn't change the fact that it's still a cat. And we would say, well, for these two images, we are hoping to get the same results from our classifier. So that's very straightforward. Flipping and cropping, you can combine these ideas, right? Now you can go ahead and take random crops of the image. That's already a little bit more sophisticated, right? Because now getting from these kind of things and still making sure that you're getting the same feature than for this kind of stuff, you see that this already creates burden to the network in a sense. And when I say burden, burden means that the training actually gets harder, right? Because for the training, it has to make sure in this optimization, what we're doing, that this image and that image gets the same features, such that, not exactly the same features, but it gets the same score functions at the end and gets the same classification results. And this is also, again, it's similar to other regularization techniques. When I say burden, I mean, let's make the training harder, right? So in this case, we're saying, well, we're adding more constraints to the training by adding more training data, right? We're basically multiplying the training data by having various augmentations of it. So this makes the training harder, but we're hoping that because it is harder now, we can channelize better to unseen samples, right? So a lot of people still confuse that, and they'd say, well, okay, we make augmentation that makes the training easier, but that's actually not true. It's the opposite. Augmentation and regularization in general makes training harder because we're having more data in this case to deal with. So we're having more constraints in our optimization, right? So we have the same number of unknown variables in our neural network. And in the optimization then means we have more constraints to follow, right? We have to make sure that these images all give you the same scores at the end of the day. Okay, so these are very simple augmentations. We're going to talk about a few more. One thing you will often see is that images here are 224 squared. That's a reason because the first convolutional neural network architectures that use ReLU-based functions in the 2010-ish years, they basically had an architecture that used this specific resolution as input. So this has nothing to do that this is like always what you want to use. But the reason why you often see this 224 squared is that a lot of architectures based on how they design, they're taking these kind of input images. Specifically, this paper by Alex Kruszewski, which is like we'll later see, it's called AlexNet. That paper was using such a resolution. So this is not always the same thing, but just for you to know where these numbers are actually coming from. Okay, so data augmentations make training harder, learn invariances and force learning these invariances specifically. And simple things are flipping and cropping and all kind of combinations of that. Other things, what people want to do is random brightness and contrast changes. This kind of makes sense as well, because these are actually things that you will see a network having to be invariant to. So in other words, if we're having like a digital camera, right, you're taking photos, people have different brightness and contrast settings, and then also people do different post-processing in the image, in the computational imaging stack that runs on the respective camera or phone or whatever, right? So it kind of makes sense to have random brightness being applied, and random contrast changes also to be applied. So this also kind of makes sense, right? Also very important here, like I think what's kind of funny is that humans are particularly good. Like we are very good at like being invariant to these kind of things. Like even if we see a cartoon and we have never seen a cartoon of a specific animal before, we're typically pretty good at generalizing to these new domains. And for networks, well, we have to train the networks in a similar way, right? So we have, like, we don't have this natural generalization though. So now we have to train the network and actually show training samples that makes sure that different brightnesses, different contrasts actually should give you the same results. Okay. Yeah, data augmentation with random crops. We've talked about this a little bit already. So training random crops, pick a random number basically, right, between the image, resize the training image, and then sample random crops of this resolution. And again, this was the resolution that was used in this AlexNet paper, but in principle, like that always has to be adapted to whatever architecture you're using, right? There's also other things you can do. I'm not going to go into too much detail. In principle, you can also do these kind of things by having different crops at test time and then average kind of the results at test time. But we're not going to talk about this one in more detail. At this point, we're going to talk about augmentation as a way to make the training better. And for testing, we're not going to change anything. Okay. And people, of course, they try to automate this kind of stuff, right? So when we're talking about data augmentation in an advanced setting, there's two kind of cool papers. There's the rand augment paper and this trivial augment paper. These are relatively recent papers. I wouldn't say this is like, not everybody uses specifically these two papers, but these two papers, they give a pretty good insight how to automate it. And basically what's happening there is you have a bunch of operations, right? You have things like auto contrast, shearing, and various other transformations. And for most of these transformations, you're going to have a selection, which one you choose. And for a specific transformation, you're then going to have a strength, like how much you want to apply that. And the idea basically is, in all of these methods, you basically go ahead and you sample which augmentation is it. Then you sample a random strength, how strong you should apply it. Then you apply the transformation, and then you're training on that specific image. And that's shared across all of these kind of auto augmentation methods. And what I already mentioned is that for the most part, people do this in the data loader actually, right? So they don't pre-compute all of these augmentations. So in other words, every time you're loading an image, you're actually randomly changing the image to a certain degree. And you're getting like an augmented image. And from that augmented image, you're doing the respective training. And now there's different ways of how to sample from these distributions, meaning that, well, you want to make sure that every image gets augmented at least n times. You want to make sure that this doesn't change anything there in the underlying distributions that you actually care about. So that's kind of critical though. Okay, when we're talking about augmentation, one thing that is really important is, like, think about augmentation and data preprocessing as a different way, like separated basically out from the architecture, right? So like this is really orthogonal. Like one thing I see also often is that people go ahead and say, oh, my network performs much better, but you're using not the same training data. And if you're applying augmentation, obviously it's not the same training data. So this is maybe a general advice. Whenever you're debugging neural networks, it's very important that you're doing debugging based on, you're doing debugging essentially based on one axis individually first. And one thing is, for instance, I want to optimize what's my best network architecture, like how many layers, how many parameters and stuff like that. Another axis might be how do I pre-process my data, right? How do I normalize it? How do I augment it and stuff like that? That's another axis. So it's very important that when you're comparing two networks and two results of your experiments, you use the same augmentation. We probably will talk about this a bit, but one thing is really important when you're debugging these networks, generally speaking, is to understand that a lot of these ideas that we're applying here are very empirical. In other words, we're going to always have an hypothesis like, oh, we might be overfitting. And then we're trying to do more augmentation and see if we do overfitting less, right? And stuff like that is always very empirical. So we always have an hypothesis. We're running a few experiments. We're making sure that we can run these experiments very quickly. Then we're looking at our train well curves. We see if they confirm our hypothesis, and then we're moving on, right? And this is kind of how you develop your architectures, how you develop your training procedures, your hyperparameters, and so on. And here it's very important, right? Data augmentation, consider it part of your network design, but when you're debugging it, make sure that it's orthogonally evaluated from things like architectural changes, right? Okay, but I hope augmentation kind of makes sense, right? So it's a type of regularization that makes sure that we're forcing the network to learn certain invariances, and we're doing it by randomly, automatically sampling it at data loading time, such that we can, we can basically get more data, make the training harder, to regularize it more, and then hopefully have less overfitting issues. Okay, so let's talk a bit more about regularization. Some regularization we talked already about the previous methods, but it's still the same concept what we would like to apply here. Regularization for the most part means make the training harder so we don't overfit, and that means that we generalize better to unseen samples. Regularization, make it harder to train. Also, when you do regularization, obviously the training loss will go up, right? Like there's no reason to expect that during training, your training loss will go down. This would make no sense because you're adding more constraints to your optimization. The more constraints you're adding to your optimization, the harder it's for the network to, quote unquote, memorize all of these ones. But that might be good, right? Because then we might actually generalize better. Okay, so we already talked a bit about L1 and L2 regularization. The one thing people want to use in practice for the most part is we want to have an L2 regularization on the weights. What does it mean? Well, when we're doing a gradient update step, we basically have here a gradient of the L2 regularization that says, well, from our weights, we want to make sure we have small weights. Or in other words, if we are having an L2 term here, what an L2 term does is it penalizes outlier weights that are too large. If you have a too large value in the weights, this will give you a high loss. And an L2 regularization on the weights will actually change these kind of things. And why is that good? Well, the reason why it's good is basically if I have one weight here from one input, it might actually input certain neurons, right? So the idea of an L2 regularizer is rather make sure that your weight strength is distributed across multiple neurons rather than taking just the input from one neuron. And in this case, it's forced to use a combination of multiple neurons in order to make the final output computation. So it's better to distribute the weights as equally as possible, to take all features as under consideration, and that is better for generalization, right? We talked about this a little bit, so this shouldn't be completely new to you, but L2 regularization is very critical for that kind of stuff. Okay, there's also a thing called weight decay. Weight decay is similar, but it's not always the same. Weight decay is the idea that basically every time you do an update step, you're decaying a little bit of your weights, right? And you have this exponential decay basically as you're running an update. The reason why it's not always the same, so in a standard gradient descent optimizer, like this would be the same, right? Because you basically every time you're making an update step and reducing it slightly. But in Atom or any advanced SGD method, it's not quite the same because like the velocity in these kind of things, they are being, the momentum and stuff like this, they're being updated slightly differently. But the idea is still the same thing, right? We don't want to have too large weights. If we're having too large weights, then we would just focus on a small subset of features. And if you're focusing just on a small subset of features, we unfortunately would get not the best results ever in terms of generalization. Right? So this is very obvious. The next thing what we can do, we can think about early stopping. Early stopping means we're monitoring our training curves and we're checking at some point, oh, our validation isn't go down anymore. So we know, well, this green curve is actually what we care about. We would like to have the lowest error here, or the lowest loss here, from the validation perspective. And early stopping would mean we say, oh, here we're overfitting, and then here we're just stopping the training here, right? We would not train any longer. And this is a very delicate procedure, by the way, because when you're stopping could make a big difference. Personally, I would always try to make sure we're adding rather more regularization in terms of L2, weight decay, stuff like that, or more augmentation to make the training harder that way. Early stopping is a thing that people do use, but it's not the most elegant thing ever, right? Because it's basically saying, well, you know, we have an optimization, we ran it, but we don't fully run it till convergence. Otherwise, we wouldn't generalize that well anymore. So there's a bit of a double-edged sword here when we're doing stuff like early stopping. So the better strategy probably than early stopping here would be to just generate more augmentations, add more, you know, weight regularization, and so on. So this would probably be better. And if you're having a training curve that looks like this one, I'm pretty sure you did something wrong in your data anyway, because that loss here, the training loss, should not go down that much. But I still wanted to mention it, that early stopping in certain cases, specifically when you don't have a lot of data, it might still make sense. Again, not very elegant, but sometimes it still might make sense, actually. Okay. Next thing. Another way to look at this is bagging and ensemble methods. So that's a little bit different. Bagging and ensemble methods, they can lead to a certain way of regularization. But the key idea there is actually to improve globally the performance of a neural network. And how would you say that? Well, since we already know that the training is actually, you know, not always deterministic, right? There's a randomness, how we sample, how we initialize weights and stuff like that. So what might happen is that sometimes our training performs a little bit better and sometimes performs a little bit worse. And even when it performs similarly, what might happen is that during the training, sometimes certain training samples perform better than others, or certain validation samples perform better than others. And the reason there is very simple. Like, for instance, if we're taking SGD as an optimizer and we're randomly sampling from the data, we're having a bias towards the samples that we've seen later on. Like, if we've seen certain samples later in our training procedure, we would expect the network to perform better there because this is what the SGD optimizer has seen last. Now, bagging and ensemble methods kind of try and exploit that and say, well, you know, if I train a model and I train it a couple of times and always I'm going to get different results, maybe it makes sense to train just multiple models and then just average out their results at test time. So, right, I train, let's say, 10 models, and from these 10 models, I'm getting a bunch of predictions, and I'm now taking the average of these predictions. I can do sort of a voting, for instance, with respect to the classes, right? I can even go further. I can even say, oh, I'm using different methods for optimization, different hyperparameters, change even the loss function and stuff like that, right? So if the errors basically are then uncorrelated, the expected combined error will decrease linearly with respect to the sample size. This one I would take with caution. It's not always linear, of course. But the idea is, of course, now, well, since we have multiple methods or multiple models, we're training all of them together. We would hope that we are getting better results at the end of the day if we're combining the results of all of them. So now you can see, this obviously takes a lot of more compute, right? Because we have to train multiple models. But typically when you do bagging and ensemble methods, you would actually get a bit of a boost in performance. Now, maybe to give you a bit of an expectation here, like this is something what people don't start with doing at the beginning because this is takes a lot of effort. This is something you would do when you have already trained a bunch of stuff, you already know your architectures pretty well and so on. So when everything else is final, things like that, you would do only at the very end. And when people compete in like benchmarks and stuff like this, like the ImageNet competition and so on, like these kind of methods here, they would actually be quite a difference. They would make a little bit of a difference, and they would make quite a difference in how high you can get up in these benchmarks. But from an absolute perspective, you get like 1 or 2% or so at the end of the day when you're trying ensemble and bagging methods, right? So it does help, but it's not fundamentally making things work or not. So when you're debugging your first networks, you would never use that, practically speaking, right? And the reason is very straightforward is like if your network gets like 90 or 91%, for you that might not matter too much right now. For somebody who competes in a benchmark and wants to make a real world application, maybe that would make a difference and then he would throw it. But what you can see already here is like with these kind of methods, you have to throw an exceptionally high amount of effort with retraining stuff at it to get a marginal gain. So there's at the beginning, you would never start with that. You would always start with simple things. But it is still important and people do use it. Okay, you can even go further and do bagging using different data sets, right? You can have different training sets and you train multiple networks on different training sets. And then you do the same idea and do some voting or some averaging of the resulting outputs. And then basically get better results at the end of the day. But again, here's the same issue. You could also argue why not use a bigger network and throw all of them together in the same data set. For the most part, different training sets is not what people use. I think for the most part, people do bagging, do ensemble methods by running it multiple times with different hyperparameters and then averaging the results afterwards. So this helps typically get a few percent, but again, it takes a lot of compute extra. So the one thing though is people thought about this a bit and they realized, well, the idea of bagging and ensemble methods does help. But maybe there's a way to get rid of this massive overhead in terms of computer free training so many methods. And one way to do that is called Dropout. Dropout is a super, super elegant way to do kind of the same thing what ensemble methods are doing, but without having to retrain so many methods. Well, so what's the idea? Well, the idea is I'm going to take a neural network. I have here a bunch of MLPs, right? I have a lot of dense connections here. And this network you can train. This network gives you something. And the idea now of Dropout is you're going to say, well, I'm just going to randomly drop a bunch of these connections in this network, right? So I'm going to go from here to here. So I'm dropping, let's say, half of my connections in my network. And that means, in this case, my network got a lot smaller, right? So my network doesn't have the same capacity in a sense anymore because I don't have the same number of weights that are currently being trained and receiving updates through training. So for training, it's going to be a lot harder to achieve the same effect. So that network will not achieve the same effect in this network, right? And that's now something that is making training harder, but I'm taking a bit of capacity away, right? So like I'm taking capacity away, so my network is not as strong anymore. I'm basically using a smaller network to achieve the same results. Now, I actually don't want to take capacity away, but what I would love to do is I would like to kind of have this ensemble of networks that is being trained and yet keep the same network structure together. And this is what Dropout doing is now, what we're doing now is we're not disabling these weights here permanently. I'm just disabling it for one update step in my training process. So the idea is every time you train and do an update step, you're randomly disabling a set of neurons, right? And this just cycles through, right? Every time you run it, every time you're disabling a different thing. So at the end of the day, all neurons will be trained, but basically we have this nice property that we're still regularizing it out and kind of mimicking what an ensemble method is doing. So think about it, Dropout is doing, it's kind of having an infinite number of ensembles within one network, right? Yeah, and then every time you run it, you basically have the idea here that you randomly drop something out. Okay, so what's the intuition now? Well, the intuition here is we basically, let's say we have half of the network. Let's say we use a dropout rate, and there's a thing called dropout rate. Dropout rate tells you what's the probability of dropping a neuron. So let's say we have a dropout rate of 0.5. That means we're using half of the network, which means it's half of the capacity. The idea there is right now very simple, actually. The intuition is saying we have a dog here, and we want to classify that dog. And for this dog image, we're going to get a bunch of features. So these features can be at the beginning or can be intermediate neurons. And the idea what we want to do is we want to have the combination of these features should tell me that this is a dog image. So I want to look at all of these features at the same time and want to make sure that I predict it's a dog. Now, what might happen though is, and that's very similar to the L2 regularization, what might happen here is that the network just has one dominant feature that makes it so easy to classify that this is a dog that the other features will simply be ignored. So if it's furry and has a tail or whatever, that would be enough to say it's a dog, right? And it would ignore the other features. And Dropout tries to counter that. So Dropout tries to say, well, I'm just not going to give you all of these features for my current pass. Make sure you train the other features too. Make sure you look at those features as well, right? So, and this way you're building up a redundant representation. So with a random subset of features, the network is forced to, during training, is forced to make the same predictions, right? And this basically means that you can't have dominant features. And this counts not just for the input features, this counts also for features further down in your network, right? And this is basically a similar effect as L2 regularization that says, well, you can't just rely on one feature, but rather you have to rely on multiple features. And this is enforced here through this dropping out of neurons during training, right? Yeah. And if you're summarizing that, right, these redundant representations, they basically help you to make sure you leverage all features simultaneously. And that's really important. It's kind of the same idea as the ensemble, right? So the ensemble is the second interpretation here. So now we basically have two models in one, or n models in one, right? Like we have this model here, that is this one, and we have this model here, that is that one. So we have like two models with half the capacity, but in one model. But as we have seen now, this model can basically take a random subset of the features, and based on this random subset of the features, it can make the same predictions, or it's forced, or it's at least trying during training to make the same predictions, right? Yeah, that's the idea of dropout, right? So we basically say this model has to make the same thing than this model, and it's actually not just two models in one, but since we are randomly dropping all these neurons, the idea is that we have an infinite number of models that of course share some overlap inside of one model. That's kind of the idea behind that, right? Okay, yeah, so if you're considering it this way, it's training basically a large ensemble of models shared on different set of data on the mini batches with shared parameters, because totally we always have shared parameters, right? And globally speaking, this reduces basically the co-adaptation between the neurons, right? So it makes sure that all the neurons are being used and not just a few neurons. Okay, so now we know how training works. You basically randomly drop neurons with dropout, and you're forcing it to have this redundant feature representation that is being learned. But now we have to make sure also we do testing. Now, at testing, we want to keep all the neurons, right? We want to make sure that all the neurons are actually turned on. And we just disable dropout at test time, right? We say, make sure we have all neurons dropped. We have no neurons dropped and everything is being used. Now we want to use actually all features, right? For test time. Now the problem is, of course, at test time, the train and the test time conditions are not the same anymore. Why are they not the same anymore? Well, the thing you will realize very quickly is, now, since we have all neurons turned on, the expected value of the distribution you're getting throughout the activations is changed, right? Since we have more neurons, the total sum of all the activations will be higher. So we have to correct for that. The way you do this correction in PyTorch is you either say model train or model eval mode. By the way, this is a very common bug that a lot of people forget. If you forget this, basically nothing will work. Now we still have to know what's going on under the hood here when we do eval mode. Well, if you're running Dropout, what that means is at test time, I said the expected value is going to change, right? So we have here our two inputs here, right? We have two weights. And what happens is if we just run the expected value through that, we will see that there's a factor of 2 coming. So this factor of 2 here is basically based on the dropout rate. So our dropout rate will scale respectively our expected value in the output. And because of that, we have to change that. So all we have to do basically is we have to do the weight scaling based on the inference. And in this case, this is our dropout probability of 0.5, right? Dropout probability of 0.5 means this one will change by 1/2. And that means we have to fix that and account for that factor, right? And if you change the dropout probability or the dropout rate, then you also have to change the respective correction that you're running at test time, right? Intuitively, this kind of makes sense, right? If I have half of my neurons disabled in the training pass, then my activations will be only half the size. So when I do it at training, I also need to, and now I use all the neurons, I need to just downscale my activations by 1/2, respectively, in order to compensate for that distribution change. Okay. All right. So yeah, I think that's basically Dropout. And Dropout is actually super important. It can be used for a lot of cool things. So it's basically an efficient bagging method with parameter sharing. Try it out. It's one line of code change, right? It's really straightforward. Dropout reduces the effective capacity of the model. That's the downside. It needs more training time because the training becomes harder. But you basically have an ensemble of smaller models inside of your big model that you're training, right? And at test time, you're still using all of the features and all of the neurons again. So it's a very efficient regularization method that a lot of people are actually using in practice, and it's still being used quite a bit. It can be used with L2 in combination, but that's just when you have too much overfitting. The standard stuff you try out is L2 regularization, dropout, augmentation. These are the standard things you typically would try out, right? Okay, so dropout nowadays. This nowadays changes every year basically, or every half a year. So one downside is Dropout doesn't work so well with batch norm. Batch norm is one thing we're going to talk about next. Batch norm is looking at the distributions of the activations basically. That's one downside. But batch norm is also a bit of a controversial thing. Sometimes people swear they have to use batch norm. Sometimes they swear they don't have to use batch norm. Let's talk about this in the second part of the lecture here. Training takes a bit longer. Usually 1.5x. I guess it depends what dropout rate you have, but as I said, training becomes harder, so you have to train longer. So that's a little bit of a downside. In practice, it's not a big thing, because practically when you have to do heavy regularization, it's when you don't have a lot of data, and then training doesn't really pose the limitation effectively, right? Okay. There's another really cool thing that is independent of the things we have been doing right now. Dropout can actually also be used for uncertainty estimation. And that's one thing I wanted to talk about right now, to just give you a bit of an idea what that means. Well, and that's a thing called Monte Carlo dropout. So Monte Carlo dropout is basically applying dropout and then looking at this ensemble of models that Dropout encodes and checking how consistent the predictions are. In fact, it's really straightforward. So Monte Carlo dropout basically does the following idea. You're running a network at test time in dropout mode, and you're checking how many times the network predicts the same stuff. If it always predicts the same stuff, the network is very confident. If the network always predicts different stuff, the network is very unconfident, right? And this is what Monte Carlo dropout is doing. So Monte Carlo dropout is not a way to get better training or whatever. It's basically just a way to get confidences for training. Confidence for certain predictions at test time. Yeah. And the idea there is to look basically at the entropy. It's looking at the inference. Then you're running this model multiple times, and you're checking how much the various runs actually change over time. So there's a bunch of theories around this, like how to look at this. This Yarin Gall's work is probably he and his team, they have started this, and they're still looking at this. And I think this is really cool actually, because that in a lot of applications it's very useful to have a confidence of how well the networks work. Right? Remember, a lot of people they claim neural networks are kind of a black box. That's something I disagree with anyway, because actually it's a well-defined optimization, and for the most part we know what's going on there. But Monte Carlo Dropout is very useful because it tells you a confidence estimate that you can apply. And the argument here is that Monte Carlo Dropouts is better than looking at, for instance, at decision boundaries such that the score functions of a softmax or so, right? Anyway, this is very useful. So I can encourage you to look at one of these papers. I think this uncertainty in deep learning is probably a good paper to look into. But you can just Google Monte Carlo Dropout and check out Yarin's paper here, which I think is really cool. Okay, all right. That's basic regularization, what we have done so far. Now I mentioned the other thing is, I mentioned already batch normalization. And batch normalization is kind of following up what we've been doing in the last lecture when we talked about initialization of neural network weights. So the problem, what you basically want to avoid is, you want to avoid that your distributions just shift throughout the layers. So you want to make sure that no matter, remember when we had the weights, we wanted to make sure that based on the weights, when we randomly initialize it, we kind of keep the distributions of our activations throughout layers by layers, and they don't drift apart. Batch normalization is the analog to that, but looking at the concrete data exactly, right? So we want to reduce the internal covariate shift basically across the layers. So what is that actually? What is the shift, right? The shift is what we had seen previously, right? We would like to make sure that the change is the distribution of network activations due to the change of network parameters during training, right? So if we stabilize the input values for each layer, then we want to prevent our activation functions from putting our input values into the max min values of the activations, right? We want to make sure that we always in the optimal range where our activation functions, irrespective of what activation function we're using now, performs well, right? And the idea is basically it should look like that, right? Everything should be our ideal scenario is everything should look like a perfect unit Gaussian. And it shouldn't look like this. This one is not good. Now everything is squished together. We're not using a real distribution here anymore. So this has a terrible coverage shift here, right? Okay. So we don't want the activations to die out. We always want to get gradients. And the way we're making sure this happens is we make sure that the distributions across the different layers, they roughly stay always the same. And batch normalization is exactly doing that. So batch normalization, the wish that we have is we want to wish unit Gaussian activations in our example. And we would love to just enforce it. So we would like to make sure that after every layer, if we're feeding a bunch of data in, our distribution always follows a Gaussian. It's very straightforward. And one way to do that is we just apply the simple formula here, right? We have the expected value of our data distribution, right? So we mean center it, and then we normalize it by the variance. That's all we do. Then by definition, we follow a Gaussian distribution here, right? And we want to do this across of all our features. And so we have this two-dimensional diagram in a sense right now. So we have the number of features. They should follow a Gaussian distribution across every feature. And we have to compute this distribution somehow. And this distribution we typically compute across our mini batch size. So all this stuff here is now being computed on a per mini batch size, right? So all of these features, they should show this distribution. We have here, then this becomes the mean of our mini batch size over our features. And then this one by definition will become a unit Gaussian, right? So in each dimension of the features, you then have a unit Gaussian as we have seen now in our example. And that's what we want to do. Every feature, in every feature dimension, we want to make sure we have a unit Gaussian, right? It's very straightforward. We just mean correct it, we divide by the variance, technically we divide by the standard deviation, and then we're getting a unit Gaussian, right? Okay, so now in each dimension of the features, you have this Gaussian. And why is that useful? Well, the idea is then we can stack basically a lot of layers together and we don't get this covariate shift, which is what we want to avoid here. And that means we get still good activations because our activations don't saturate out or relos don't die out and stuff like that. Okay, so batch normalization normalizes the mean and the variance of the inputs in the activation functions. And then what you do is practically you now have these batch norm layers. So you have an MLP basically, so a fully connected layer. You have a batch norm activation, fully connected layer, batch norm activation, right? And this is very common what people are using right now. So they're using, later that we're going to see this also in the combination of convolutional networks. We haven't talked about this yet. But the idea is basically what you do is you first have layer with weights, then you do batch norm, and then you feed it in the activation. And this batch norm block is usually done in this order. For instance, it wouldn't make sense to have the batch norm after the activation. You want to have this Gaussian normalization before you're feeding it into your activation function. Because the whole point is we want to make sure that whatever we're feeding in our activation stays in an active regime and gives us good gradient activation, good gradients for our optimization, right? Okay, so how does this work in practice? Well, in practice, we have to backpropagate this whole thing, right? So this is a differential function, so we can just backpropagate it. You can already see it becomes a little bit more complicated. If you have a large batch, right, you have to now consider all samples at the same time. So it has a bit of a drawback, right? We'll talk about the drawbacks a little bit later. But the second thing what the batch norm is doing, it also allows the network to change the range here, right? So you have a second update step that takes this normalization here and says, oh, you can change the range here throughout the backpropagation. So you're adding two more hyperparameters here. You're adding two more learnable parameters here. This beta and this gamma here that scales the Gaussian and adds a bias to it basically, right? And the idea here is that the network can learn to undo the normalization depending on the needs. So you give the network more flexibility. So you don't have this hard-coded normalization. So you're saying like, oh, the network should be normalized as much as you can, but if you need to deviate, please do so. Now we have these two hyperparameters here. And typically, what you could imagine, if this one is the variance, or the standard deviation here, and this one is the expected value, then this one cancels out here. Then we have the original distribution here, right? And this is kind of the idea that the batch norm is normalizing, but then it can learn how to change the normalization, how much we need it actually. So the default is normalize the unit Gaussian and then allow it to change it to some degree. And these ones are learnable parameters. These are learnable parameters that we backpropagate through, and we're optimizing them simultaneously. Okay. Right. So this is basically batch normalization. I can only say a few pros and cons here, right? I mean, the pro is very obvious, right? We want to make sure that every layer gives you activations that follow a Gaussian distribution. We allow it to deviate from it with these two with these two learnable parameters here. And then we're feeding into the activation, and the hope is that since it's closer to a Gaussian, then you're gonna get better activation ranges for our activations, and we get better gradients, and we can stack more layers together. I should say there's one disadvantage here, of course. One drawback here is that we have to go now over the entire mini batch to do these backpropagations. That, you know, is computationally comes with a bit of a burden. Not crazy, but to some degree. And it might be a little bit unstable. So if your estimate of the variance and the expected value here is not ideal within your mini batches, and you have a bit of unstable samples, then batch normalization might make the training also a bit unstable. And this is something that happens from time to time. Right. So maybe a recommendation here. So my recommendation, generally speaking, here is never start using batch normalization at the beginning. Batch normalization is something you want to add later on. So batch normalization makes the training often a bit unstable, and it can give you great performance boosts, but it comes at a price in terms of engineering it. So yeah, that's something you should know. But it's a very common layer that is being added to a lot of like very deep neural network layers, very deep neural network architectures. Okay, so a couple of more things here. So batch normalization, is it okay to treat dimensions separately? I mean, people just doing it and it works. So conversion is still faster with this method. There's a bunch of people that try to analyze it mathematically. We're not going to go into that one, but in practice, it just works pretty well, right? And then the second thing what we haven't talked about is we haven't talked about training versus test time. So versus training time, the mean and the variance is estimated over the mini batch. That's what I said, right? It's a bit of a drawback because you have to consider the whole mini batch, and that's one issue. So at test time, we don't have mini batches, right? We're only running a single image at the same time. So now we don't have a chance to compute a meaningful mean and variance. And in practice, what people are doing there, they're just doing the same trick what people have done for like the optimizers itself. So they're using momentum basically to figure that out. So what you do is you compute a mean and a variance from a mini batch during training. And then during testing, you compute the mean and the variance by running an exponentially weighted average across training and across training throughout the mini batches. And then you have these two hyperparameters of the variance and the mean. And that one you just use for the testing then afterwards. And the way you do this is the same way you're computing the momentum in our favorite optimizers, right? For instance, like in Atom or so, right? It's just this exponentially weighted average, what you're computing there. Okay. So we're now getting very deep networks. They are, easier to train. This one is not 100% clear. It depends a bit. You're definitely getting more stable gradients for the most part. Much larger networks in principle can be trained with it. And so in principle, batch norm is a way that helps a lot. And you can see that also that, specifically like these resonant architectures we're going to talk about, Inception architectures, these things that we're using it. So you see that, like this is the top one arrow on ImageNet, by the way. And this is the year, like this is going until 2018. So there's a bit of a debate. Like you use them, you get better numbers, but you would probably not start to develop your methods with it. That's what I wanted to say there. So batch norm is a big milestone. It's very important because you can train very large networks with it. Another drawback to consider here is the batch size is critical. If the batch size is too small, then this estimate of the variance is not great, right? So in this case, you want to basically use as large batches as possible. So the larger the batches, the better stuff trains, basically. There's other normalizations that follow the same concept. One is called group norm. The group norm is trying to counteract this issue here. Basically, you don't want to be so dependent on your batch size anymore. And the whole point is that it's always the same point between all of these normalizations. So normalization says make sure that the distributions between the input and the output of a layer stay always the same, and such that we're normalizing it, such that we're getting good activations when we're passing it through our activation function, right? We're getting good gradients when we're passing it through, right? So the way this basically works is you can think about it this way. What kind of normalizations you can do? There's a couple of different ones actually. There's batch norm we've just talked about. There's layer norm, instance norm, and group norm. Group norm was this one that works pretty well apparently. But the whole point is basically like this. So if you're thinking about this is the input tensor to a layer, right? Like let's say this is an image, width and height. This is the feature channels, right, that you care about. And what batch norm is now doing is like over all the samples in a mini batch, it treats every feature channel independently, right? So this feature channel has nothing to do with the other feature channel. So you're computing the batch norm independently for one feature. And for the next feature, you would do the same thing and so on. This is what batch norm is doing. Layer norm does the exact same thing. This is the image size, yeah. So layer norm is doing the exact same thing, except it doesn't do it over different samples. It does it within the channels of one sample, right? Instance norm does it within one sample, but across the different values within one image. And the group norm now does it with parts of that. It doesn't do it with all the features, but it does it with a bunch of features. And this is the number of features, and this is the number of elements in a mini batch. Sorry, should have shown this before. But the whole idea is what I'm trying to say here is these normalizations, they all have the same idea. Like the whole idea here is you always want to make sure that your activations are getting good distributions. So, and for these good distributions, you're applying some normalizations after applying a linear layer, or after applying the weights, before the nonlinearity, you're applying the respective normalization. And now you can slice this cube basically between the feature dimensionality, the C here, right, the number of samples in a mini batch, and the image sizes. You can now slice this cube in kind of all kind of ways. And all of these have drawbacks and advantages, right? Batch norm, we have said, well, okay, you need a large mini batch because you need to go over all of these ones here. Group norm counters it and says, well, okay, we don't care about this. We just go across the feature channels and so on. So the whole point is we're just trying to get a good estimate for variance for the normalization there, right, throughout the variances. And that helps us to get good regimes for our activation functions. And the way we get there, we're taking all kind of various slices here in order to get good estimates here, right? So I mean, there's two things that are important. I think you should still know what batch norm, layer norm, instance norm, group norm does. So have a look at this one concretely. But I think it's even more important to understand the high-level concept here. The high-level concept here is basically you slicing this cube in various ways to get good estimates here of variance expectation value. Then you can do normalizations with that. And depending on what architecture, what data and stuff like this you're using, these ones might be different. And batch norm is very relying on batch size, right? Okay. Right. So with that, we've gone through quite a few things now. Maybe a quick summary, what we know right now, because we're mostly at the end of this lecture. It's a little bit shorter today. What we know now is we have networks. We have like width and height of a network, right? We have output layers. We know what neurons are. We know the idea of like we have a linear part and a nonlinear part of a neuron. We have different kinds of activation functions. Some work better, some work worse. We know how to compute gradients. We know how to do backpropagation very efficiently. We know how to optimize with SGD variations. Like Adam is probably our method of choice here. And we know various types of augmentations, like data augmentation, batch, and then regularizers, such as dropout, weight regularization. We know weight initialization. We know batch norm now, stuff like that. So one thing we will notice now is, in principle, we know all the theory right now about neural networks. Not all the theory, but we know a lot of theory already. The one thing we will know, what we have done right now, it doesn't scale very well. It has a bit of an issue. You can't just stack more layers together. And that's a thing people have realized very quickly. Because what we're doing right now is we're just stacking like this brute force connection of neurons together. We have no structure in the network. And so we have good universal function approximators with neural networks, but the generalization is hard because we have no structure. And structure is kind of the thing what we're going to talk about next, right? Currently, it's very brute force, and the optimization becomes harder to get to the right results. So we need more structure. And more structure is what we're going to start with in the next week. We're going to talk about CNNs, convolutional networks. We're going to talk about recurrent neural networks. And eventually, one thing that a lot of people have heard a lot about probably already is transformers. So all of these ideas here, what we're doing now is we're bringing more structure to our networks. And for those who don't know it, CNNs, this is the way how you do typical classification. RNNs is typically what you're using for natural language processing stuff. And transformers is, it's also for NLP things like ChatGPT and stuff like this. They're built on transformer architectures. All right. So with that, we're concluding today. I hope this was fun. There's a lot of practical things we have talked about today. Try them out. Thanks for joining. and see you everybody next week. See you and bye-bye.